Welcome, everyone. Today, we're diving into the fascinating world of differential equations. This is the cover slide, so I just want to start by saying how excited I am to take you through this topic. The title of our presentation is Differential Equations, and we'll also explore some key concepts and applications along the way. Over the next few slides, we'll look at what differential equations are, how they work, and why they're so important in various fields. So, let's get started and explore this intriguing subject together. Let's take a look at the steps involved in solving a first-order linear differential equation. First, it's essential to understand the different types of differential equations we'll encounter. We start with equations that are separable, where the variables can be isolated on opposite sides, making the solution process more straightforward. Next, we classify differential equations according to their order, which tells us the highest derivative present. This helps us determine the complexity of the problem and the methods we'll use. We also classify them based on their linearity, whether the equation is linear or nonlinear, which influences the solution techniques. Another important concept is forming a family of curves from a differential equation. This perspective helps us understand the general solution and how particular solutions relate to initial conditions. We then look at linear differential equations specifically, as they have well-established methods for solutions. Homogeneous equations are a special case where the solutions can be simplified further, often leading to more elegant solutions. Understanding the difference between general and particular solutions is crucial because the general solution contains arbitrary constants, representing the entire family of solutions, while the particular solution fits specific initial conditions. Finally, we consider the degree of a differential equation, which is related to the highest power of the highest derivative in the equation, and the overall solution process, which involves a systematic approach to find the explicit functions satisfying the differential equation. All these points connect to give us a comprehensive framework for approaching and solving first-order linear differential equations efficiently. Let's take a closer look at the classifications of differential equations. As we discussed earlier, differential equations can be categorized based on certain characteristics. First, we have their linearity, which refers to whether the equation involves only the unknown function and its derivatives in a linear way. Then, there's the aspect of order, which tells us the highest derivative present in the equation. These classifications are fundamental because they influence the methods we use to solve different types of differential equations. Understanding these categories helps us navigate the complexity and select the appropriate approach for each problem. So, in summary, the classifications depend mainly on linearity and order, and grasping these concepts is key to mastering differential equations. When we talk about differential equations of order 2 or more, we refer to them as higher-order differential equations. These are equations where the derivatives involved go beyond just the first derivative, involving second derivatives, third derivatives, or even higher. They tend to be more complex, but they are very important because they can model more intricate systems in engineering, physics, and other sciences. Now, focusing on first-order differential equations, these are the simplest kind. They involve only the first derivative of the dependent variable. That means the equation describes how the function changes at a particular point without involving higher derivatives. Understanding these classifications based on order helps us organize the solutions and approaches we use. It's a fundamental step in understanding differential equations as a whole, because the order directly influences the methods we'll need to solve these equations. So in this slide, we're highlighting the distinction. Higher-order equations involve derivatives of order 2 or more, while first-order equations involve just the first derivative. Recognizing this difference is key as we move forward in solving and applying these equations to real-world problems. A function which satisfies the given differential equation is called its solution. So, when we talk about solving a differential equation, we're essentially looking for that specific function or set of functions that make the equation true. This means if we plug the function into the equation, both sides will be equal, confirming that it's a solution. Understanding what a solution looks like helps us interpret the behavior of systems modeled by differential equations. It's a fundamental concept because finding the solution is often our main goal in solving these equations, connecting the theory directly to real-world applications. Now, let's talk about the difference between the general and particular solutions of a differential equation. The general solution is the one that includes arbitrary constants, which means it has some unknowns that can take any value. This solution essentially represents a family of solutions, covering all possible behaviors of the differential equation. When we assign specific values to these arbitrary constants, we get a particular solution. This particular solution is free from arbitrary constants and satisfies specific initial conditions or boundary conditions. So, in essence, the general solution gives us the broad picture, while the particular solution zooms in on a specific case. Understanding this distinction is key because it helps us see how solutions can be tailored to particular problems or conditions, which ties back to the overall theme of solving differential equations effectively. Let's consider a family of curves, which we denote as F2, and assume it depends on parameters, say a and. In this case, the family can be represented by an equation of the form F2 of x, y, a and b equals 0. This equation encapsulates how the shape and position of the curves vary as we change the parameters a and b. Now, if we look at a different family, called F1, which depends on only a single parameter, then its equation can be written as F1 of x, y, a equals 0. This simpler dependence often makes it easier to analyze and work with the family. The key idea here is that the dependence on parameters allows us to generate a whole set of curves from a single equation by varying those parameters. And this concept plays a crucial role when we move toward forming differential equations for families of curves, which is our next step in understanding their behavior more deeply. Now let's talk about differential equations with variables separable. If we have a function f of x and y, and it can be written as a product of two functions, g of x and h of y, then we say that the differential equation dy/dx equals f x, y is of variable separable type. Essentially, this means we can split the equation into parts that depend only on x, and only on y. This separation makes the equation much easier to solve, because we can integrate each side separately. It's a powerful technique that's very useful when dealing with many real-world problems where the variables can be isolated like this. Recognizing when a differential equation is separable helps us choose the right approach and simplifies the solution process, which ties back to the overall theme of understanding different methods to solve differential equations efficiently. Now, let's move on to homogeneous differential equations. These are a special class of differential equations that have a particular structure. Essentially, a differential equation is called homogeneous if all the terms are of the same degree, or more specifically, if the equation can be written in a form where every term involves the dependent variable or its derivatives in a consistent way. In simpler terms, these equations often have a form that allows us to make a substitution, which simplifies solving the problem. Recognizing whether an equation is homogeneous is important because it guides us toward the most effective method of solving it. This concept ties into our overall goal of understanding different types of differential equations and their solutions. Let's take a closer look at what a first-order linear differential equation really is. It has this specific form: dy/dx plus p times y equals q. Here, p and q are either constants or functions that depend only on. The key point is that these equations are linear in y and its derivative, which makes them easier to handle and solve. Recognizing this form is important because it allows us to apply a set of methods specifically designed for linear equations. This concept ties into the overall theme of differential equations, where understanding the structure helps us choose the right approach. So, in essence, identifying these linear forms is a critical step in solving many real-world problems modeled by differential equations. Now, let's focus on the classification of differential equations based on their linearity. A differential equation is called a linear differential equation when the dependent variable and its derivatives appear only to the first power, and importantly, they are not multiplied together. This means that the equation can be written in a form where each term involving the unknown function or its derivatives is simple and straightforward. On the other hand, if the dependent variable or its derivatives are involved in any nonlinear way, say, multiplied together or raised to a power other than 1, then the differential equation is considered nonlinear. Understanding whether a differential equation is linear or nonlinear is crucial because it influences the methods we use to solve them and the types of solutions we can expect. So, recognizing these key differences helps us better approach the broader classification of differential equations and their solution strategies. Now, let's look at the solution of the differential equation. It is given by the formula x times the integrating factor, which equals the integral of q times the integrating factor with respect to y, plus a constant c. It's important to note that if our differential equation is in the form dx/dy plus p1 times x equals q1, where p1 and q1 are either constants or functions of y only, then the integrating factor, if, is expressed as e raised to the integral of p1 with respect to y. Once we have the integrating factor, we multiply through the differential equation to make it easier to solve. The solution then becomes y times the integrating factor equals the integral of q times the integrating factor with respect to x, plus the constant c. In practice, to solve a first-order linear differential equation, we first write it in the standard form dy/dx plus p times y equals q, where p and q depend only on x. Next, we find the integrating factor by calculating e to the power of the integral of p with respect to x. Finally, we multiply the entire differential equation by this integrating factor, which simplifies it into an exact differential. Then, we can integrate to find the solution, adding the constant of integration. So these are the key steps: rewriting the equation in the proper form, finding the integrating factor, and then integrating to obtain the solution. This systematic approach makes solving these differential equations much more manageable.